Tonight, we're going to talk about a shortcut through the universe that Einstein himself accidentally discovered and then almost immediately dismissed. A tunnel that could connect two distant points in space without crossing the distance between them. Fold the fabric of the cosmos in half. Punch a hole through both layers and travel from one side to the other. It sounds like something pulled straight out of science fiction, and for decades, most physicists treated it that way. But the equations don't lie, and the equations say wormholes are allowed. They've been sitting there since 1916, buried inside the very first exact solution anyone ever found to Einstein's field equations, waiting for someone to notice what they actually meant. By the end of tonight, you're going to understand exactly what a wormhole is in the language of physics, what it would take for one to exist, why every attempt to build one keeps running into the same wall, and why the answer to the deepest question about it is more interesting and more unsettling than anything science fiction has ever bothered to explain. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with space itself. Not space as a backdrop for things that happen. Not space as the emptiness between objects. Space as a physical object in its own right. This is the first shift in thinking that general relativity demands, and it's the one most people never fully make. In everyday experience, space feels like nothing. It's the absence of stuff. You move through it, things exist inside it, but space itself doesn't do anything. It just sits there, passively, while physics happens inside it. Isaac Newton thought about it this way. He treated space as a fixed, unchanging stage on which objects moved and forces acted. The stage was given. The stage was eternal. The stage didn't participate in any of the action. Objects moved through it. Gravity pulled between them across it. But the stage itself was just there. Albert Einstein dismantled that picture completely. In his general theory of relativity, published in 1915, after roughly a decade of work, space and time are not the stage on which physics happens. They are players in the physics. Together, they form a single four-dimensional structure that Einstein called space-time. And that structure is not fixed and passive and eternal. It is physical. It curves. It stretches. It compresses. It ripples. It bends in response to everything that exists inside it. Mass warps space-time. Energy warps space-time. Momentum warps space-time. Pressure warps space-time. Anything with mass or energy tells the space-time around it how to curve, and that curving is what we experience as gravity. The sun does not pull Earth toward it through some invisible force reaching across empty space, the way Newton thought. The sun curves the space-time around it. Earth follows the straightest possible path through that curved geometry. What looks like an orbit, from the perspective of familiar Euclidean space, is actually Earth taking the most direct route available through a landscape that is itself bent by mass. A straight line in a curved space-time. This is not a metaphor or an analogy. This is the geometry. The planets orbit the sun because the sun has bent the local geometry of space-time so severely that the straightest possible path through it curves back around. Light bends around massive objects for exactly the same reason. Light also follows the straightest possible path through space-time, and near a very massive object, that path is curved, because space-time itself is curved. You can measure this. You can observe it. Astronomers routinely watch background galaxies appear distorted and multiplied around intervening clusters of galaxies, the light bent by the gravity of all the mass in between. Gravitational lensing, a direct consequence of the geometry. And once you accept that space-time is a physical structure, that it bends and curves and responds to what's inside it, a certain question becomes not just possible but inevitable. If space-time can curve, can it fold? Can it develop topology? Can two points that are distant from each other in the ordinary sense be connected by a shortcut through the structure itself? The answer to that question begins with a solution to Einstein's field equations, worked out almost immediately after Einstein published them. In 1916, a German physicist named Karl Schwarzschild was serving as an artillery officer on the Eastern Front during the First World War. Under conditions that are remarkable to contemplate, far from any physics library or university, in the middle of an active military campaign, Schwarzschild solved Einstein's field equations for the simplest possible case. A single point of mass, perfectly spherical, utterly alone in an otherwise empty universe. He solved the equations exactly, in closed form. His solution described the geometry of space-time around such an isolated massive object with extraordinary mathematical precision, and it made predictions. It said how much the path of a light beam would bend as it passed near a massive object. It said how the orbit of Mercury would precess slowly, a small rotation of the ellipse over centuries, in a way that Newton's theory couldn't fully explain, and that had puzzled astronomers for decades. It said how strongly clocks would slow down in stronger gravitational fields, a prediction that seems strange until you realize that time itself is part of the space-time structure that curved space-time is distorting. Schwarzschild sent his solution to Einstein in a letter. Einstein was astonished. He had privately believed that the field equations were too complex to admit exact solutions and that physicists would have to work with approximations. Schwarzschild's result was published in early 1916. Schwarzschild himself passed away a few months later from an illness contracted at the front. He never saw how far his equations would reach, because buried inside the Schwarzschild solution, deeper than anyone appreciated at the time, was something that would take decades to fully understand. Something that looked, at first glance, like a minor technical feature of the mathematics. A small peculiarity. A detail to be handled carefully. What it actually was a tunnel. Every massive object in the Schwarzschild solution has a radius associated with it. A critical threshold. Below this threshold, the gravitational pull becomes so extreme that nothing, not even light, can move fast enough to escape outward. This threshold is the Schwarzschild radius. For an object as massive as the Sun, the Schwarzschild radius works out to about 2.9 kilometers. The actual Sun is vastly larger than this, nearly 700,000 kilometers across. So the extreme region is buried deep inside, where the Sun's own plasma holds things up against further collapse. No problem. The singularity stays hypothetical. But compress the Sun below 2.9 kilometers, crush all that mass into a sphere smaller than a city, and you get something very different. The region inside the Schwarzschild radius becomes completely cut off from the exterior. No signal can escape from inside to outside. Not light, not radio waves, not any particle moving at any speed, because all of them would need to move faster than light to escape, and nothing can do that. The boundary of this region, the Schwarzschild radius itself, is what we now call the event horizon of a black hole. In 1916, most physicists treated this as a mathematical curiosity. Surely, nature would never compress a star that severely. Surely something would intervene to prevent the collapse before it reached that extreme. This assumption was wrong, and it would take until the 1960s for physicists like John Wheeler, Roger Penrose, and Stephen Hawking to establish that black hole formation is actually a natural consequence of stellar evolution. But the more immediate point for tonight is not what happens outside the Schwarzschild radius. It's what the geometry looks like inside, and what you find when you extend the mathematics fully and carefully, when you trace all possible paths through the space-time rather than just the ones that stay safely outside, is something deeply unexpected. The geometry doesn't just describe a one-sided pit in space-time. It describes a tunnel, a passage between two separate regions. And this feature of the geometry is exactly what Einstein and Rosen found in 1935. Albert Einstein and his collaborator, Nathan Rosen, approached the Schwarzschild solution with a specific question in mind. They were not, primarily, thinking about black holes or tunnels or shortcuts through space. They were trying to solve a different problem. They wanted to know whether the equations of general relativity could describe elementary particles, objects like electrons and protons, as geometric structures in space-time, rather than as separate things that happen to exist inside space-time. This was a beautiful idea. Instead of treating a particle as something that sits in space-time and produces a field around itself, what if the particle actually was a knot or a handle in the fabric of space-time? What if the electron was just a particularly interesting wrinkle in the geometry? This approach didn't ultimately work. The attempt ran into obstacles that proved too severe, and the program was eventually set aside. But in exploring it, Einstein and Rosen looked at the Schwarzschild geometry more carefully than anyone had before. And what they found was that the solution, when extended to its full mathematical form, rather than just the region outside the event horizon, doesn't just have one exterior. It has two completely separate exterior regions of space-time. Each one looks, from its own outside, like an ordinary open universe. Normal space-time, normal physics, a place where you could, in principle, live and work without noticing anything strange about your surroundings. But connecting the two exterior regions at the deepest point of the geometry is a narrow throat, a bridge, a tube in the structure of space-time linking the two otherwise disconnected regions. Einstein and Rosen called it an Einstein-Rosen bridge. Today, physicists call it a wormhole. Now, pause on what this actually means. Einstein and Rosen were not speculating. They were not proposing a new theoretical idea or adding something to general relativity. They were reading what the equations already contained. The most basic, most fundamental, most elegant solution to Einstein's field equations, the simplest possible case of a single spherical mass, produces a geometry that looks like a tunnel between two regions of space-time. This is what the mathematics says. It has always said this. It said it in 1916, the moment Schwarzschild published his solution. Nobody noticed until 1935. And even then, nobody understood for a long time what it really implied. Because the tunnel, as Einstein and Rosen discovered, has a serious problem. Here's what the Einstein-Rosen bridge actually looks like geometrically. Physicists use what's called an embedding diagram to visualize it. Take a two-dimensional slice through the full four-dimensional space-time, freeze time, and look at just the spatial geometry at one moment. What you see in that slice looks like two flat sheets connected by a narrow tube. Each sheet represents one of the two exterior regions. The tube between them is the wormhole throat. The whole structure resembles two funnel shapes, joined at their narrow ends. Each opening is a mouth. The narrow middle section is the throat. In between the two mouths, the throat connects two otherwise separate parts of the geometry. Those two parts might be two different regions of the same universe, very far apart in ordinary space, but connected through the wormhole interior. Or they might be two entirely separate universes, with no path between them in ordinary space at all, linked only through this bridge. General relativity doesn't specify which. The equations permit both. And this ambiguity is not a flaw in the theory. It's a reflection of the fact that general relativity describes local geometry extremely precisely, but says almost nothing about the overall global topology of space-time. Whether the universe is simply connected like an infinite flat space where there's only one way to get from here to there, or multiply connected, like a torus where you can go around in a loop and come back to where you started, is not determined by the local equations. It's a boundary condition, a question about the universe's global structure that the theory leaves open. And the Schwarzschild solution, in its maximally extended form, describes a space-time with a non-trivial topology. A topology that includes the bridge. But here's the devastating part. The bridge doesn't stay open. This is the problem that Einstein and Rosen noticed, and that became clear to everyone who worked through the geometry carefully in the following decades. The Einstein-Rosen bridge is not stable. It exists in the mathematics at one moment, and then it collapses. The throat pinches off. Not slowly, over some finite time that a traveler might race through. Essentially, instantly. The throat closes before any particle, any signal, any amount of information could cross from one side to the other. Why? Because the geometry of the Schwarzschild solution is dynamic. Even though it describes what looks like a static, unchanging spacetime, the interior geometry is not frozen. It evolves. The throat is not a stable equilibrium. It's a moment in a process of continuous collapse. If you tried to enter the wormhole from one mouth, you would cross the event horizon of a black hole. Everything from that point on would be exactly what any observer crossing a black hole event horizon would experience. You fall inward. The geometry becomes more severely curved. The singularity approaches. The throat, which you might have hoped to pass through, snaps shut before you reach it. You don't emerge on the other side. You encounter the singularity. Physics, as we understand it, stops giving meaningful answers. This isn't a technological limitation. You couldn't fix it with better propulsion or faster acceleration. The throat closes faster than light. And in relativity, nothing outruns light. No matter how fast you enter the wormhole, the throat will close before you reach the other side. This was the state of wormhole physics from 1935 until the late 1980s. The tunnel is real in the mathematics. The tunnel is impassable in the physics. That seemed to be the end of it. Then Carl Sagan called Kip Thorne. In 1985, Carl Sagan was finishing a science fiction novel called Contact. It was the story of a radio astronomer named Ellie Arroway, who detects a signal from an extraterrestrial intelligence and eventually travels to meet them. For the journey, Sagan had written wormholes into the plot. Sagan was not a physicist who would carelessly insert bad science into a novel. He was a scientist first, deeply committed to accuracy. Before publication, he called his friend Kip Thorne at Caltech, one of the world's leading experts in general relativity, and asked him a specific question. Was a traversable wormhole consistent with physics? Not the Einstein-Rosen bridge. Not the collapsing throat of the Schwarzschild solution. Something different. A stable wormhole that a spacecraft could actually enter and exit. A tunnel that a person could survive traveling through. Was this physically possible? Thorne didn't answer immediately. He sat with the question. And then he brought in his graduate student, Michael Morris, and the two of them began working through the problem systematically and rigorously. They didn't ask whether the specific Schwarzschild wormhole was traversable because they already knew it wasn't. They asked a more fundamental question. Is there any solution to Einstein's field equations, any space-time geometry whatsoever, that functions as a traversable wormhole? A stable throat. Openings on each end. Tidal forces inside the throat, small enough that a human being wouldn't be pulled apart. Transit time short enough to be practical. Gravitational time dilation modest enough that the traveler wouldn't age differently from people outside. They laid out the conditions carefully and looked for geometries that satisfied them. The answer they arrived at was technically yes. But attached to that yes was a condition so extreme that it created an entirely new set of problems. And understanding that condition requires a detour into quantum mechanics. To understand what Morris and Thorne found, you need to understand how Einstein's equations work as a two-sided relationship. On one side of the field equations is the Einstein tensor, which is a mathematical object encoding the curvature of space-time, the geometry. On the other side is the stress-energy tensor, encoding the distribution of mass, energy, pressure, and momentum. The matter and energy content of space-time. The equations say these two things are proportional to each other. Geometry determines matter. Matter determines geometry. If you specify what the matter looks like, the equations tell you what geometry it produces. If you specify a geometry you want, the equations tell you exactly what kind of matter and energy distribution you'd need to produce it. For a traversable wormhole geometry, Morris and Thorne worked out what the stress-energy tensor had to look like at the throat. The answer was something that had never been observed in any laboratory, never detected in any astronomical measurement, never confirmed to exist in any form anywhere in the observable universe. The throat of a traversable wormhole requires matter with negative energy density. Not very low energy. Not zero energy. Negative. Below zero. This substance, whatever it might be, has less energy than empty space itself, and its effect on space-time is the opposite of ordinary mass. Ordinary mass curves space-time inward. It creates gravitational attraction. It draws things toward it. This exotic negative energy substance curves space-time outward. It pushes rather than pulls. It creates a kind of anti-gravity, and it's this outward push that could, in principle, hold the wormhole throat open. The natural tendency of the throat is to collapse. Every quantum of energy crossing the threshold, every bit of radiation entering the wormhole, pushes inward and accelerates the collapse. To counteract this, you need something at the throat that pushes back. Ordinary matter makes things worse. Exotic matter with negative energy could make things better, could counteract the collapse. could maintain the geometry in an open, stable, traversable configuration. The physics is logically self-consistent. The mathematics is clean. But the question of whether exotic matter actually exists in the universe was not answered by the Morris Thorne paper. And the question of how much of it you'd need revealed just how severe the problem really is. Before getting to the quantity problem, it's worth addressing the more basic question. Does negative energy density actually exist anywhere in physics? Or is it purely theoretical? The surprising answer is that negative energy density is real. It has been measured in laboratories. It's a genuine quantum mechanical phenomenon. To understand it, you need to think carefully about what empty space is. Classical physics says empty space is exactly that, empty. No matter, no energy, no fields. The vacuum is zero. Quantum mechanics says something very different. In quantum field theory, the framework that successfully combines quantum mechanics with special relativity, particles are not fundamental objects. They're excitations of underlying quantum fields that permeate all of space-time. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The Higgs boson is a ripple in the Higgs field. These fields are present everywhere. They fill all of space, and they're subject to quantum uncertainty. Werner Heisenberg's uncertainty principle, formulated in 1927, says that certain pairs of physical quantities cannot simultaneously be known with arbitrary precision. The more precisely you know the position of a particle, the less precisely you can know its momentum. The more precisely you know the energy of a system at a given moment, the less precisely you can know the timing of that energy. This isn't a limitation of measurement technology. It's a fundamental feature of nature. Quantum fields have a version of this uncertainty that applies to the field value and its rate of change. You can't simultaneously know both with perfect precision, which means the energy of a quantum field in its lowest possible state, the vacuum, cannot be exactly zero. If it were exactly zero, that would require both the field value and its rate of change to be precisely zero simultaneously, which would violate the uncertainty principle. So, instead, the vacuum fluctuates. The field energy is uncertain. It oscillates around its average. Virtual particle-antiparticle pairs appear and annihilate. The vacuum is not nothing. It's a seething medium of quantum fluctuations. We call it vacuum energy, zero-point energy, the energy of the lowest quantum state. And its effects are completely measurable. The Casimir effect is the most famous example. It was predicted by the Dutch physicist Hendrik Casimir in 1948. Here is the setup. Take two uncharged metal plates. Make them parallel. Place them very close together, separated by a gap on the order of nanometers. Between the plates, the vacuum fluctuations are constrained. Only certain wavelengths of the quantum fields can fit in the narrow gap. The geometry restricts which modes of the vacuum can exist there. Outside the plates, in the open space around them, the full spectrum of vacuum fluctuations exists with no such constraint. This creates an asymmetry. There is more vacuum energy outside the plates than between them. The result is a net pressure pushing the plates together. A tiny but very real force. A force arising from nothing but the geometry of the quantum vacuum. Casimir predicted it. And, in 1997, Steve Lamoureau at the University of Washington measured it directly. The measurement matched the theoretical prediction to within 5%. It has since been confirmed many times, with improving precision, in many different experimental setups. The Casimir effect is real. And what matters for wormholes is this. The energy density of the vacuum between the plates is negative compared to the vacuum outside. The region between the plates has less energy than completely empty space. Negative energy density. Real. Measured. Confirmed. Not hypothetical. Not science fiction. A phenomenon you can produce in a laboratory right now with metal plates, a micrometer adjustment, and a sensitive force detector. So, exotic matter, the negative energy substance that a traversable wormhole requires, is not something forbidden by physics. It's something that quantum mechanics naturally produces. The question is only whether it can ever be produced in quantities large enough to matter. And here, the numbers are severe. Morris and Thorne worked out estimates for the exotic matter requirements, and the picture is not encouraging. The amount of negative energy needed depends on the size of the wormhole. For a wormhole throat with a radius of about 1 meter, large enough for a person to pass through, various calculations over the years have converged on requirements in the range of negative energy comparable to the mass energy of a planet-sized object. Some analyses suggest it needs to be concentrated in a thin shell around the throat. Others suggest it needs to be distributed through the interior. The precise number depends on the exact geometry. But the scale is consistent, enormous. The Casimir effect, in the most optimistic laboratory setup, produces negative energy densities at the scale of microjoules per cubic meter in the gap between plates. To hold open a traversable wormhole with a 1 meter throat, you'd need negative energy at a scale many, many orders of magnitude larger. The gap between what quantum mechanics delivers in laboratory conditions and what a traversable wormhole requires is not something that incremental engineering progress could bridge. It's a gap so large that crossing it would require physics we don't currently have any idea how to do. And there's a deeper theoretical concern beyond just the quantity. In the 1970s, physicists developed a set of mathematical constraints called energy conditions. These are statements about the properties that physically reasonable matter and energy should satisfy. The weak energy condition says no observer should measure a negative energy density at their location. The null energy condition says that energy density plus pressure in any direction should never be negative. The dominant energy condition says energy should never flow faster than light. The strong energy condition says that gravity should always be attractive in a precise mathematical sense. Ordinary matter satisfies all of these. Every form of matter and energy we've ever directly observed in a laboratory satisfies all of them in normal conditions. And a traversable wormhole requires violating the null energy condition at the throat, not as an optional feature, as a structural requirement. Without this violation, the throat collapses. With the violation, the throat can remain open. The null energy condition is violated by quantum mechanics in small ways. The Casimir effect is technically a violation of it, locally, between the plates. So the violation is not absolutely forbidden. But scaling it up from the Casimir regime to the astrophysical regime required for a useful wormhole is a problem that nobody has solved. In 2022, researchers published results suggesting that quantum corrections near the wormhole throat actually require even more exotic matter than classical estimates suggested. The problem is getting harder as physicists look more carefully, not easier. This is not encouraging for anyone hoping to engineer a wormhole. But it's also not the end of the story. Because in the 1980s and 90s, something important happened to wormhole physics that shifted the focus from engineering to something more fundamental. The realization that wormholes and black holes are connected in ways nobody had anticipated. Let's go back to what happens inside a real black hole, not the idealized Schwarzschild case. A real astrophysical black hole, the kind that forms when a massive star exhausts its nuclear fuel and its core collapses. Or the kind that grows at the center of a galaxy, fed by infalling gas and dust and the occasional star that wanders too close. Real black holes rotate. Not because physicists chose to add rotation to the model, because stars rotate, and when a rotating star collapses, conservation of angular momentum causes the resulting black hole to rotate too. The geometry of a rotating black hole is described not by the Schwarzschild solution, but by the Kerr metric, worked out in 1963 by New Zealand mathematician Roy Kerr. It took nearly half a century after Einstein published general relativity to find the exact solution for a rotating black hole. The Schwarzschild solution for a non-rotating black hole had been found almost immediately. The Kerr solution required more mathematical sophistication. But when Kerr found it, it revealed something striking. The interior structure of a rotating black hole is fundamentally different from a non-rotating one. In the Schwarzschild case, the singularity at the center is a point, or more precisely, a spatial region extended in time, a one-dimensional line in space-time. In the Kerr case, the singularity is not a point at all. It's a ring. A closed loop in space, around which the rotation axis passes. And this ring singularity has a property that point singularities don't. Mathematically, there are trajectories through the Kerr geometry that thread through the ring, passing through the plane of the ring without hitting the singularity itself, and continuing into a new region of space-time on the other side. The Kerr metric, fully extended, describes not just one exterior universe, but potentially multiple regions, connected through the rotating black hole's interior. This looks, mathematically, like a wormhole structure, a passage from one region to another through the interior of a rotating black hole. But here, the same problem that plagued the Einstein-Rosen bridge appears again, in a different form. The interior of a real rotating black hole is not described by the idealized Kerr metric. The Kerr metric is a vacuum solution. It assumes complete emptiness outside the singularity. A real rotating black hole is not empty inside. It's been forming from real matter and radiation. Infalling matter continues to cross the horizon. Radiation from outside gets blue-shifted to enormous energies as it falls inward. In the 1980s and 90s, physicists worked out what happens to the Kerr geometry when you add these perturbations. The answer, developed in detail by Eric Poisson, Werner, Israel, and others, is called mass inflation. As infalling matter and radiation approach a particular region of the Kerr interior called the Cauchy horizon or inner horizon, the geometry there becomes violently unstable. Small perturbations amplify exponentially. The space-time curvature diverges. The inner horizon, and with it, any wormhole-like passage through the rotating black hole, is destroyed. Not slowly degraded, destroyed completely. By the time any would-be wormhole traveler arrived at the region where the passage might have existed, the geometry would have been violently disrupted by the mass inflation instability. The wormhole structure of the idealized Kerr solution appears to be an artifact of idealization. Real rotating black holes, with their messy real-world interiors, probably don't contain passable wormhole structures. So, The two most obvious sources of natural wormholes, Schwarzschild black holes and Kerr black holes, both fail. The Schwarzschild bridge collapses too fast to traverse. The Kerr bridge is destroyed by instabilities before anything can reach it. The universe, it seems, is not in the habit of making wormholes the obvious way. But the universe has surprised physicists before. And in the early 21st century, a completely unexpected connection emerged between wormholes and something that seemed at first completely unrelated. Quantum information. In 2013, Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford published a short paper that proposed something remarkable. Two phenomena that had appeared to have nothing to do with each other might actually be the same thing. The two phenomena were the Einstein-Rosen bridge, the wormhole, and what is known as EPR entanglement. Quantum entanglement, as described in a famous 1935 paper by Einstein, Podolsky, and Rosen. The conjecture is stated simply: ER equals EPR. Einstein-Rosen bridge equals Einstein-Podolsky-Rosen correlation. Wormhole equals entanglement. To understand why this is a serious proposal rather than a metaphor, you need to understand what quantum entanglement actually is. When two particles interact, they can enter a quantum state that cannot be described as two separate individual particle states. Their quantum properties become correlated in a specific way. If you measure the spin of one particle and find it pointing up, you instantly know that its entangled partner will show spin pointing down when measured, regardless of where the partner is. This correlation exists, no matter how far apart the particles are. There is no distance at which the entanglement goes away. It's instantaneous and non-local. Einstein hated this. He called it spooky action at a distance. He thought it proved that quantum mechanics was incomplete, that there had to be some hidden variable, some local reality, that quantum mechanics was failing to capture. He was wrong. Experiments testing Bell's inequality, first by Friedman and Clauser in 1972, and then decisively by Alan Aspect and collaborators in the early 1980s, proved that the correlations are exactly as quantum mechanics predict. There are no hidden variables. The entanglement is real. The non-local correlation is a genuine feature of the world. It cannot be used to send information faster than light, because the outcome of each individual measurement is random. Only by comparing results afterward, through ordinary, slower-than-light communication, do the correlations become visible. But the entanglement itself is a genuine physical relationship between the two particles. Whatever the two particles are doing with each other, they're doing it across any distance, instantly. Maldacena and Susskind argued that this relationship has a geometric meaning. That the entanglement between two particles, or more dramatically between two black holes, corresponds to the existence of an Einstein-Rosen bridge connecting them. Two entangled black holes are, in this picture, connected by a wormhole. Not metaphorically, not analogically, actually connected. An Einstein-Rosen bridge threading between their interiors. The entanglement is the wormhole. The wormhole is the entanglement. Two descriptions of the same underlying reality, one in the language of quantum information and one in the language of space-time geometry. If the ER equals EPR conjecture is correct, the implications are extraordinary. Consider what it says about ordinary matter. Any two particles that have ever interacted with each other and become entangled are, in this picture, connected by a tiny wormhole. not a wormhole you could travel through. Not even a wormhole you could detect with any existing instrument. A Planck-scale bridge, smaller than any probe we could use, part of the quantum microstructure of space-time. The fabric of space-time, at its smallest scales, would be threaded with these connections. Not the smooth continuum that general relativity describes, but a network. A complex, high-dimensional web of entanglement links, each pair of entangled particles connected by a microscopic bridge. The large-scale smooth space-time we experience would be an emergent property of this network, arising from the collective behavior of astronomically many entanglement connections. The way the smooth flow of a river emerges from the collective motion of water molecules. Space-time, in this picture, is not the fundamental thing. Entanglement is the fundamental thing. Space-time is what entanglement looks like when you zoom out. Geometry is a consequence of information. This is a profoundly different picture of reality than anything in classical physics. Einstein thought of space-time as the fundamental stage. The ER equals EPR. Conjecture says that space-time is built from quantum correlations, that the connections between distant regions, the distances and angles and curves of the geometry, are all expressions of the pattern of entanglement in the underlying quantum system. Remove entanglement, and space-time would dissolve. Disconnect the quantum correlations, and the geometric structure that emerges from them would vanish. The universe, on this view, is not fundamentally geometric. It's fundamentally informational. The geometry is secondary. A large-scale consequence. This idea connects directly to one of the deepest unsolved problems in all of physics: the black hole information paradox. It has been the central puzzle of theoretical physics for nearly half a century. Here's the setup. In 1974, Stephen Hawking showed that black holes are not perfectly black. Quantum mechanics implies that black holes slowly emit radiation, now called Hawking radiation. This radiation arises from quantum effects near the event horizon. Pairs of virtual particles continuously pop into existence everywhere in space. Near the event horizon, one member of a pair can fall inside while the other escapes outward. The escaping particle carries energy, so it's real radiation. The infalling particle has negative energy, so it slightly reduces the mass of the black hole. Over astronomical timescales, a black hole slowly loses mass and eventually evaporates completely. The Hawking radiation is thermal. It looks like the radiation emitted by a hot object with a specific temperature. And crucially, it appears to carry no information about what fell into the black hole. If you threw a book into a black hole and waited for the black hole to evaporate, the Hawking radiation that came out would not contain the information from the book. The information would be gone. But quantum mechanics is fundamentally a theory about information. One of its most basic principles is that information cannot be destroyed. Quantum processes are reversible in principle. If you know the exact state of a system and the laws governing its evolution, you can always recover the past state. Information is conserved. General relativity says information falls into the singularity and is destroyed. Quantum mechanics says information cannot be destroyed. These two statements are in direct contradiction, and both theories are very well established. Something has to give. This is the information paradox. It has generated decades of fierce debate. A bet between Stephen Hawking and John Preskill was conceded by Hawking in 2004, when he accepted that information probably escapes, though the mechanism was unclear. Hawking proposed various ways information might escape. None of them were universally accepted. The ER equals EPR conjecture offers a possible resolution. In the conjecture, the Hawking radiation that escapes a black hole is entangled with the interior of the black hole. The interior and the radiation are connected by quantum wormholes. The information from what fell into the black hole is not destroyed at the singularity. It's encoded in the subtle quantum correlations of the Hawking radiation, connected to the interior through the entanglement structure. The wormhole maintains the connection. The information escapes, not in the usual Hawking radiation, but in the quantum correlations between the radiation and the interior. This is deeply technical and relies on mathematical machinery that goes beyond what can be explained simply. But the core idea is that wormholes are not just a curiosity about exotic spacetimes. They might be the mechanism by which quantum mechanics and general relativity are reconciled. The bridge between the two great frameworks, both literally and figuratively. In 2017, Ping Gao, Daniel Jafferis, and Aaron Wall published theoretical work showing that an ER equals EPR wormhole could be made traversable through a quantum mechanical manipulation, not exotic matter. A quantum protocol. Here's the setup, simplified. You have two entangled black holes. By the ER equals EPR conjecture, they're connected by a wormhole. Normally, this wormhole is not traversable. The same reasons that make Einstein-Rosen bridges impassable apply here. The throat collapses before anything can cross. But Gao, Jafferis, and Wall showed that if you perform a specific quantum operation on the two black holes simultaneously, a coupled interaction between particles escaping from the two sides, you can briefly render the wormhole traversable. The key is that the quantum coupling sends negative energy into the wormhole throat, not classical exotic matter. Quantum energy, associated with the quantum state modification that acts like exotic matter in the relevant sense. For a brief window, the throat opens. A quantum particle inside the wormhole can traverse it and emerge on the other side. This works because the coupling effectively signals the wormhole that a particular quantum state should be on the other side. The particle doesn't travel through conventional space. It travels through the wormhole, which is shortcut for it. And crucially, what emerges from the wormhole has the same quantum information as what would have arrived through quantum teleportation. A different quantum protocol that uses entanglement to transfer quantum states. The wormhole, traversal, and quantum teleportation give you the same outcome. Different paths. Same destination. Same information. This is one of the most striking pieces of evidence for ER equals EPR. The two things that the conjecture claims are the same, wormholes and entanglement, give you identical results when you try to use them. The wormhole and the quantum channel are not just analogous. They're operationally equivalent. In 2022, a team of researchers from Google and Caltech implemented a version of this protocol on a quantum computer. Using 9 qubits and a specific quantum circuit designed to simulate the relevant physics, they created what they described as a traversable wormhole. The experiment generated enormous press coverage. Headlines around the world declared that scientists had created a wormhole. The physics community was more careful. What the experiment did was implement, on a quantum processor, the mathematical equations that govern traversable wormhole physics in a simplified two-dimensional model of quantum gravity. The quantum computer executed a simulation of a specific quantum system that exhibits the same dynamics as a wormhole in this mathematical framework. A quantum signal was sent in one side of the simulation and detected emerging on the other side, with correlations matching the predictions of wormhole traversal. But the quantum computer was not curving physical space-time. It was not creating any geometric tunnel in the fabric of the universe. It was not moving any particle through any physical wormhole. It was solving equations. Very interesting equations. Equations that describe wormhole physics in a precisely defined mathematical setting. Equations that are formally equivalent to the dynamics of entanglement in a certain quantum theory of gravity. The researchers understood this distinction perfectly well. Some of the reporting did not convey it equally well. What the experiment genuinely demonstrated is that the equations governing wormhole physics and the equations governing certain quantum information processes on a quantum computer are the same. Equations. You can implement one by implementing the other. This is a formal mathematical equivalence, not a metaphor. And formal mathematical equivalences in physics tend to mean something about the underlying reality. The fact that a quantum computer can reproduce the dynamics of wormhole traversal, the fact that the same equations describe both, is evidence that the two things are descriptions of the same underlying physical phenomenon. That entanglement and wormholes are genuinely two faces of the same reality. How deep that equivalence goes, and what it implies about the existence of real macroscopic wormholes in astrophysical spacetimes, remains an open question. But the formal connection is established. It's not speculation. It's mathematics. Take stock of what physics actually knows about wormholes. Not what's speculated. Not what's hoped. What's established. General relativity is the best-tested theory in the history of physics. Every prediction it has made has been confirmed by experiment. The bending of light around massive objects was observed in 1919 by Arthur Eddington during a total solar eclipse. He measured the apparent positions of stars near the edge of the sun's disk while the sun was blocked by the moon, and found that they were shifted exactly as Einstein predicted. General relativity predicted them. Newton's theory predicted a smaller shift. Einstein won. Gravitational time dilation is real. Clocks at higher altitudes run faster than clocks at lower altitudes. The Global Positioning System uses 31 satellites in medium Earth orbit. Each satellite carries an atomic clock. These clocks run about 45 microseconds per day, faster than clocks on the ground because they're in a weaker gravitational field. At the same time, they run slower by about 7 microseconds per day due to their velocity, special relativistic time dilation. The net effect is that they gain about 38 microseconds per day. That seems tiny. It is not. Light travels about 11 meters in 38 microseconds. If the GPS system didn't correct for this, the position errors would accumulate by more than 10 kilometers per day. The GPS satellites correct for it. They implement the predictions of general relativity in real time, every day, for every device on Earth that uses GPS. The theory works. Gravitational waves were predicted by Einstein in 1916. He derived them directly from the field equations. He also suspected they would be too small to ever detect. He was wrong about that. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, two facilities separated by 3,000 kilometers in Louisiana and Washington state, detected a signal. The signal lasted about 0.2 of a second. It was the gravitational wave signature of two black holes, each about 30 solar masses, spiraling together and merging about 1.3 billion light-years away. In the fraction of a second of the final in-spiral and merger, they radiated more energy than the output of all the stars in the observable universe combined, as gravitational waves. The waves compressed and stretched the Earth by a fraction smaller than 1,000th the diameter of a proton. LIGO detected it. The waveform matched the prediction of general relativity calculated from numerical simulations. The match was extraordinary, precise, complete. The same theory, the same equations, the same framework. And this framework, which has been confirmed in every test ever performed, contains wormholes as an intrinsic feature, not added on, not speculative, written directly into the solutions of the equations. The mathematics has never been wrong. Whatever it says about the geometry of space-time is the best physical understanding we have of what space-time actually is. And it says that space-time is the kind of thing that can have tunnels in it. Now consider what we've directly observed of the most natural candidates for wormholes. Black holes. Real ones. In 2019, the Event Horizon Telescope collaboration published the first image of a black hole's shadow. The target was the supermassive black hole at the center of the galaxy Messier 87. Messier 87 is a giant elliptical galaxy about 53 million light-years away in the Virgo cluster of galaxies. The black hole at its center has a mass of 6.5 billion times the mass of the Sun. 6.5 billion solar masses. The Schwarzschild radius of an object that massive is about 19 billion kilometers, larger than our entire solar system. The Event Horizon Telescope is not a single instrument. It's a planet-scale radio telescope array, combining data from radio dishes on multiple continents using a technique called very long baseline interferometry to achieve the equivalent resolution of a telescope the size of Earth. The team observed Messier 87's central region and produced an image. What they saw was a bright ring of glowing hot gas, heated to billions of degrees as it spirals inward through the accretion disk surrounding the black hole. In the center of the ring was a dark shadow. Not completely dark, but dark enough. The shadow region corresponds to where the gravity is so strong that light cannot escape. The size and shape of the shadow match the predictions of general relativity for a black hole of 6.5 billion solar masses. In 2022, the same collaboration imaged Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A sits about 27,000 light-years from Earth. It has a mass of about 4 million solar masses, much smaller than the Messier 87 black hole, but still enormous. Its Schwarzschild radius is about 12 million kilometers, about 160 times the radius of the Sun. Imaging Sagittarius A was in some ways more difficult than imaging the Messier 87 black hole, despite it being closer, because the gas and dust surrounding it changes on much shorter timescales. The image they produced showed the same characteristic ring of glowing gas and dark central shadow, matching the predictions of general relativity. These are not inferred objects. They are directly imaged. They exist. They are real. And, according to the mathematics of the theory that has never been wrong, every one of them contains an Einstein-Rosen bridge in its interior. The tunnel is there, in the mathematics, for every black hole in the observable universe. Whether it goes anywhere, whether it leads somewhere, or collapses into the singularity, is a question that physics cannot currently answer. And any observer who crossed the event horizon to investigate could never send a report back. The deepest question about wormholes is not whether they can be engineered. It's what they tell us about the nature of space-time at its most fundamental level. And here we arrive at something that general relativity itself cannot answer: the topology of space-time. Topology is the branch of mathematics that deals not with the shape of spaces, but with their deep connectivity. Not how curved a surface is, but how it's connected, whether it has holes, whether it's simply connected, meaning any loop can be continuously shrunk to a point, or multiply connected, meaning some loops pass through handles that prevent them from shrinking. A sphere is simply connected. A torus, a donut shape, is not. If you draw a loop that goes around the whole of the donut, you can't shrink it to a point without tearing the surface. In everyday experience, space seems simply connected. There are no handles you can reach through, no loops that can't be shrunk. But general relativity says nothing about this. It specifies how space-time curves in response to matter. It says nothing about whether space-time has handles in its topology. The global structure is not determined by the local equations. It's a boundary condition, an input to the theory rather than an output. The universe might have been born with a simply connected topology and stayed that way. Or it might have had a multiply connected topology from the beginning. Or topology might change dynamically, with wormholes forming and closing as the universe evolves. General relativity, on its own, cannot tell you which. A theorem proved by Robert Garrick in 1967 says that a smooth change of spatial topology in general relativity requires either closed time-like curves, paths through space-time that loop back on themselves, or a singularity somewhere in the process. This is disturbing. If creating a wormhole, if changing the topology of space from simply connected to multiply connected, necessarily involves either a singularity or a time machine, then topology change might be extremely limited or impossible in practice. But the Garrick theorem assumes a smooth space-time manifold. It's a classical result. It might not apply in quantum gravity. At the Planck scale, the assumptions of the theorem break down. Space-time is not necessarily smooth at those scales. The quantum fluctuations of the geometry might allow topology to change in ways that the classical theorem forbids. The answer to the topology change question requires quantum gravity. And quantum gravity remains the central unsolved problem in fundamental physics. String theory is the most developed attempt to build a theory of quantum gravity. It's been under active development since the 1980s. String theory replaces point particles with one-dimensional objects called strings. The different vibrational modes of a string correspond to different particles. And, crucially, string theory automatically contains general relativity. The equations of general relativity emerge from string theory as a low-energy limit. Gravity is not put in by hand. It falls out of the mathematics. String theory also contains higher dimensional objects called branes, and it predicts more than 4 dimensions of space-time. The extra dimensions are compactified, curled up into tiny shapes too small to detect directly with current experiments. String theory has produced remarkable mathematical insights. It was the context in which the ER equals EPR conjecture was developed. It gave rise to the holographic principle, the idea that the information content of a region of space is encoded on its boundary, not its volume. It has generated deep connections between quantum gravity in certain spacetimes and quantum field theory on their boundaries. These connections, known collectively as holographic duality or AD-CFT correspondence, after the specific geometries involved, have been used to calculate properties of strongly interacting quantum matter. Properties that could not be calculated any other way. They have also been used to explore the interior structure of black holes and to make predictions about what wormholes in specific spacetimes should look like. But string theory has not been experimentally confirmed. Its predictions for new physics beyond the standard model at energies accessible to current accelerators have not been observed. The Large Hadron Collider has not found supersymmetric particles, which many versions of string theory predict. The extra dimensions have not been detected. Whether this means string theory is wrong or right, but with its new physics at energies beyond current experimental reach, remains unresolved. Loop quantum gravity is a different approach. It doesn't try to unify all forces. It tries specifically to quantize general relativity, to make spacetime itself a quantum object. In loop quantum gravity, spacetime at the Planck scale is not continuous. It's a discrete network of quantum volumes and areas. The geometry is granular. There is a smallest possible volume and a smallest possible area set by the Planck scale. Below these scales, the concepts of distance and area lose their meaning. The smooth spacetime of general relativity emerges from this granular structure at large scales, the way the smooth surface of a table emerges from the atomic lattice at small scales. In loop quantum gravity, the question of wormhole physics at the Planck scale becomes the question of what the network of discrete spacetime quanta looks like near the extreme conditions of a black hole or a potential wormhole. Throat. Loop quantum gravity predicts that singularities are resolved. The infinitely curved singularity at the center of a black hole, where classical general relativity breaks down, is replaced in loop quantum gravity by a region of extremely high but finite curvature. A quantum bounce. The collapse halts before hitting the singularity and begins to re-expand. This has implications for the interior structure of black holes and for the possibility of wormhole-like connections through them. But loop quantum gravity also has not been experimentally confirmed. Its predictions for observable consequences, such as specific modifications to the spectrum of primordial gravitational waves from the early universe, have not yet been tested with sufficient precision. Both major approaches to quantum gravity remain theoretical. Neither has been confirmed. And both of them say things about wormholes that are different from what classical general relativity says. Until one of them, or some other approach, is confirmed, the deepest questions about wormhole physics remain genuinely open. Let's be concrete about observational prospects. If a traversable wormhole existed somewhere in the universe, a natural one, formed by some process we don't yet understand. What would it look like? A wormhole mouth in space would appear as a region of gravitational lensing. Background objects behind it would be distorted, arced, and magnified, the same way objects behind a black hole are lensed. From a distance, the gravitational signature of a wormhole mouth might be difficult to distinguish from a black hole of similar mass. Both would lens background light. Both would affect the orbits of nearby stars and gas. But there's a crucial difference in the visual signature. A black hole is a one-sided gravitational sink. No light escapes from inside the horizon. The center of a black hole image is dark. A traversable wormhole mouth, by contrast, is not a one-sided sink. It's an opening. Light from the other side of the wormhole can travel through the throat and emerge from this side. If you were looking at a traversable wormhole mouth, you would see, at the center of the gravitational lensing ring, a bright region. Not darkness. The view from the other end of the wormhole. Whatever is on the other side, whether another part of our galaxy or another universe entirely, you'd see its light coming through. A window, not a shadow. This visual signature is in principle detectable. Researchers have worked out in detail what such an image would look like, how it would differ from a black hole image, and what instruments would be needed to distinguish the two. One specific proposal involves stellar orbits. The stars orbiting Sagittarius A at the center of our galaxy have been tracked for decades by the Gravity Collaboration, using the Very Large Telescope Interferometer in Chile. The star, called S2, orbits Sagittarius A with a closest approach of about 120 astronomical units and a period of about 16 years. Its orbit has been measured with exquisite precision. The measurements match the predictions of general relativity for a black hole of 4 million solar masses. If Sagittarius A were actually a wormhole rather than a black hole, the gravitational field would be different at large distances. A wormhole has mass on both sides, and both contributions affect the gravity experienced by an orbiting star. The orbital dynamics would differ from a pure black hole in specific ways. Current measurements are consistent with a black hole, but the precision of current measurements might not be sufficient to detect small deviations. Future observations with improved instruments might reveal these deviations or confirm the black hole interpretation more decisively. The Event Horizon Telescope's image of the Messier 87 black hole and Sagittarius A could in principle be compared to predictions for wormhole images. Researchers have done this comparison. The images are consistent with black holes. They don't require wormholes. But they don't definitively rule out certain wormhole configurations either. More sensitive observations at higher resolution, with longer baselines and improved detector technology, are needed. Those observations are being planned. The answer to whether Sagittarius A is a black hole or a wormhole is not yet in. Physics is watching. There is one last implication of wormhole physics that deserves attention, because it changes the way you think about the universe as a whole. If the ER equals EPR conjecture is correct, every pair of entangled particles in the universe is connected by a wormhole, and the universe is full of entanglement. Particles have been interacting and entangling since the very beginning. The quantum vacuum is full of entangled pairs. Particles interact with their environments constantly, creating entanglement with everything around them. The entanglement is everywhere. If each entanglement corresponds to a wormhole connection in the geometry, then the geometry of spacetime is built from entanglement. The connections between distant regions, the distances and angles and curves that make up the universe's spatial structure, are a consequence of the pattern of quantum correlations. The universe is, in this picture, not fundamentally a geometric object. It's fundamentally an informational object. A quantum system with an enormous number of degrees of freedom, entangled with each other in a complex pattern. The smooth space-time we experience, the space through which galaxies and stars move, the time that clocks measure, these are emergent properties. Large-scale consequences of the small-scale quantum correlations, and the wormholes that thread through space-time, connecting entangled particles and systems, are not exotic rarities. They're part of the basic fabric, part of what space-time is built from. In this view, the universe is literally woven from wormholes. Countless microscopic bridges connecting quantum degrees of freedom, their collective behavior giving rise to the geometry we experience as space and time. This is speculative. The ER equals EPR conjecture is not a proven theorem. It's a proposal, supported by significant evidence, consistent with what we know, pointing in a direction that many physicists find compelling, but unproven. Whether it's right is a question for future physics, future experiments, future mathematical proofs, future theoretical frameworks. What's not speculative is that the connection between wormholes and quantum entanglement is being actively explored by some of the most talented physicists in the world. Not as a curiosity, as a serious attempt to understand the fundamental nature of spacetime, as a possible path toward quantum gravity, as a resolution of the information paradox, as a unification of the two greatest theories of the 20th century. The work is ongoing. The results are coming in. And the direction of the work suggests that wormholes are not a peripheral idea. They're central. They're part of what space-time is. Start with the energy conditions more carefully. The null energy condition states, in precise terms, that for any light-like direction in space-time, the sum of the energy density and the pressure in that direction must be greater than or equal to 0. This sounds technical. What it means physically is this. No matter how you move, no observer, not even one moving at nearly the speed of light, should ever see the local energy density become negative enough to matter. The condition is satisfied by every form of classical matter: solids, liquids, gases, electromagnetic radiation, dark matter, in any of its proposed forms. All of them satisfy the null energy condition. The null energy condition is, in a sense, a statement that gravity is always attractive at the local level. Ordinary matter always gravitates, always pulls space-time toward it, never pushes away. A traversable wormhole requires violating this. At the throat, the energy density plus pressure in the radial direction must be negative. The geometry must be pushed outward rather than collapsing inward. And this cannot be done with ordinary matter. Period. The question becomes whether quantum mechanics provides a way. The Casimir effect violates the null energy condition locally. Between the plates, the energy density is negative enough that the null energy condition is technically violated in that region. But the Casimir effect also satisfies what are called quantum energy inequalities. These are constraints, derived by Ford and Roman in the 1990s, that limit how much negative energy can exist in a region and for how long. The negative energy between the Casimir plates is compensated for by positive energy elsewhere. The total energy, integrated over any complete region of spacetime, remains non-negative. You can borrow negative energy from the vacuum, but you have to pay it back. The quantum energy inequalities are like a bank. You can have a negative balance for a short time, but you can't maintain a permanent negative balance indefinitely. For a wormhole throat, what you need is sustained, stable, persistent negative energy density. A permanent negative balance. The quantum energy inequalities suggest this is not achievable. The Casimir effect can give you a momentary overdraft. It cannot give you the sustained negative account you'd need to hold a wormhole open indefinitely. This was worked out in detail by Ford, Roman, and others through the 1990s and 2000s. Their conclusion was that wormholes stabilized by Casimir-type effects would have to be extremely small, smaller than an atomic nucleus, possibly much smaller. Not because Casimir-type effects are too weak, but because the quantum energy inequalities mean that the negative energy can only be concentrated in a very small region with an enormous positive energy compensating it nearby. For a wormhole throat of radius much less than a proton, the exotic matter requirements might be satisfiable by quantum effects. For a wormhole throat large enough for anything to pass through, they are not. Unless something beyond the known quantum energy inequalities is at work. Something new. Something that hasn't been discovered yet. This is not impossible. Physics has been surprised before. But it requires new physics. Not just better engineering. New, currently unknown physics. Consider the stability problem from a different angle. In 1990, William Kim and Robert Wald, and independently Kip Thorne and collaborators, worked out what happens to quantum fields threading through a traversable wormhole when you try to send something through it. The analysis uses quantum field theory in curved spacetime, the same framework that produced Hawking radiation. You put a wormhole into the spacetime. You trace all the paths that vacuum fluctuations, the quantum zero-point fields of empty space, can take through the wormhole geometry. And what you find is that some of those paths loop through the wormhole, exit one mouth, travel through the exterior spacetime, and re-enter the other mouth. Closed loops. Paths that go around and come back. And on each round trip, the vacuum fluctuations pick up a phase shift, a change in their quantum state. These phases accumulate. The vacuum fluctuations interfere constructively. The energy density near the throat grows. It grows without bound as the geometry approaches the conditions needed for a closed time-like curve, a situation where the wormhole could be used for time travel. Before any traveler enters the wormhole, before any physical object crosses the throat, the quantum vacuum itself is already building up a divergent energy density at the throat. This would destroy the wormhole. Hawking argued that this was a general feature, that any spacetime with a wormhole approaching the conditions for a closed time-like curve would be destroyed by this quantum vacuum instability. This is related to the chronology protection conjecture. The spacetime protects its own causal structure by allowing the quantum vacuum to blow up any wormhole that threatens to violate it. Now, there are important caveats. These calculations were done in specific, idealized wormhole geometries. They depend on how the quantum fields are defined and renormalized near the throat. There is genuine uncertainty in the technical details. Some researchers have argued that certain wormhole geometries might evade the worst of the quantum back reaction. Others have argued that the effect is robust across many geometries. The technical debate has not fully resolved. But the general direction of the argument, that quantum effects near the wormhole throat tend to be destructive rather than helpful, has been sustained across decades of work. Adding the quantum stability problem to the exotic matter requirement, you get a picture where traversable wormholes face not one, but two independent severe obstacles. The obstacles come from completely different parts of physics. Exotic matter comes from classical and quantum thermodynamics and the structure of the stress-energy tensor. The quantum stability problem comes from quantum field theory in curved spacetime. Two separate lines of argument, both pointing in the same direction. That makes the case against traversable wormholes more serious, not less, than either obstacle alone would suggest. Now consider the problem from the perspective of entropy and thermodynamics. Black holes have thermodynamic properties. This was one of the most surprising discoveries in theoretical physics of the 1970s. Hawking and Jacob Bekenstein showed that black holes have entropy, a measure of their disorder or information content, proportional to the area of their event horizon. The Bekenstein-Hawking entropy formula relates the entropy of a black hole to the area of its horizon, divided by 4 times the square of the Planck length. This is a genuinely remarkable result. In ordinary thermodynamics, entropy is a property of the bulk of a system, growing with its volume. For black holes, entropy is a property of the surface, growing with its area. This suggested something profound about the nature of information in gravitational systems. The information content of any region of spacetime is bounded by the area of the region's boundary, not its volume. This is the holographic principle. The amount of information you can pack into a region of space is limited by its surface area in units of the Planck area. The holographic principle has deep implications for wormholes. A traversable wormhole connecting 2 regions would, in effect, allow information to move between those regions through the throat. But the holographic principle constrains how much information can flow through any surface. The throat area of the wormhole determines its information-carrying capacity, and the thermodynamic constraints suggest that wormholes can't be used to violate the second law of thermodynamics. The total entropy of any closed system can only increase or stay the same. If you tried to use a wormhole to achieve something that the second law forbids, the thermodynamic constraints would prevent it. The wormhole is not above thermodynamics. It obeys it. And the Bekenstein-Hawking entropy formula, applied to wormhole geometries, suggests that the quantum information content of a wormhole is not infinite. A wormhole of a given size can only carry a finite amount of information. The amount is set by the throat area in Planck units. This connects back to the quantum information perspective on wormholes. In the ER equals EPR picture, the capacity of an entanglement-based wormhole to transmit information is related to the amount of entanglement between the 2 sides. More entanglement, more capacity, and the entanglement is finite. Bounded, not arbitrarily large. These thermodynamic constraints don't forbid wormholes, but they place limits on what wormholes can do. They can't be used to violate thermodynamics any more than anything else can. They can't serve as information conduits of unlimited capacity, and they can't be used to circumvent the second law. The universe, in this sense, is consistent. The same laws apply everywhere. Even to the most exotic space-time structures the mathematics can produce. There is a specific type of wormhole solution that has attracted particular attention in recent years because it seems to be the most physically plausible. The traversable wormhole by coupling, the type described in the Gauss-Jaffery's wallpaper. This is a wormhole that becomes traversable not through exotic matter, but through a specific quantum coupling between the two ends. The mechanism requires sending a signal between the two sides of the wormhole through an external channel, not through the wormhole itself, through normal space. The external signal carries quantum information. It's used to perform a specific operation on one end of the wormhole. This operation effectively injects negative energy into the wormhole throat through quantum effects. The injection is controlled. It's precisely calibrated, and it opens the wormhole for a brief window. A single quantum particle can traverse the wormhole during this window. The particle emerges on the other side. What the particle carries, the information in its quantum state, is the same information that quantum teleportation would have transferred. The wormhole and the quantum channel give you the same result. This type of wormhole is not a shortcut through space in the usual sense. It's not faster than light. The signal you send between the two ends, the signal that opens the wormhole, travels through normal space at the speed of light or slower. The particle that travels through the wormhole arrives at its destination no sooner than it would have if it had simply been teleported using the normal quantum teleportation protocol. The wormhole is not a time machine. It's not faster than light. It's equivalent to quantum teleportation, which means it conveys no advantage over simply using quantum teleportation directly. This might sound disappointing. What's the point of a wormhole that doesn't save any time? But this isn't really the point of the physics. The point is that the wormhole and the teleportation channel are equivalent. They're the same thing. One described geometrically and one described in quantum information terms. The equivalence is the insight. It confirms the ER equals EPR picture. It shows that two things which appeared completely different are actually one thing seen from two angles. And this kind of unification, the recognition that apparently different phenomena are descriptions of the same underlying reality, is one of the most powerful moves in theoretical physics. It's how Maxwell unified electricity and magnetism. How Einstein unified space and time. How quantum mechanics unified the wave and particle descriptions of matter. The unification of wormholes and entanglement might be the next one. Or it might turn out to be incomplete or wrong in ways that become clear with more research. But the move is being made. The physics is pushing in this direction. And the direction is interesting. Let's step back even further and think about what it means that we're asking these questions at all. We live in a universe that, as far as we can determine, is about 13.8 billion years old. It began in an extraordinarily hot, dense state and has been expanding and cooling ever since. The first stars formed a few 100 million years after the beginning. They lived and exploded and seeded the universe with heavier elements. Galaxies assembled, evolved, merged. Generations of stars formed and ended. And after about 9 billion years of this, in an ordinary spiral galaxy, in an unremarkable corner of the cosmos, a small rocky planet formed at an appropriate distance from a middle-aged yellow star. Over the next 4.5 billion years, life emerged on that planet. It evolved. It developed nervous systems. Eventually, it developed the capacity for abstract thought, for language, for mathematics, for science. And in the last 100 years of the 14-billion-year story, creatures on that planet have discovered that the universe they live in is governed by equations that contain wormholes. That the same mathematics which describes how the sun bends light, how black holes form, how gravitational waves propagate across cosmic distances, also describes tunnels in the fabric of space-time, passages through the geometry, connections between distant regions. And those creatures are now asking, with the full seriousness of their best mathematical tools and their most precise instruments, whether those tunnels are real, whether the universe actually contains them, whether the equations that have never been wrong are pointing at something that physically exists. The fact that we can ask this question at all is itself remarkable. That the structures of human thought evolved for catching food and avoiding predators on an African savanna turn out to be capable of probing the deep geometry of space-time. That the mathematics we developed to describe the motion of objects on Earth turns out to be applicable to the structure of the universe on the largest and smallest scales. That the theories we built to describe gravity and quantum mechanics contain, buried in their implications, the possibility of tunnels through space and time. This is what makes physics strange. Not just that the universe is big, or old, or mostly empty, but that the equations that govern it are rich enough, complex enough, surprising enough to contain structures that nobody expected. Wormholes were not put into general relativity on purpose. Nobody decided to include them. They fell out of the mathematics. The way the Higgs boson fell out of the Standard Model before anyone looked for it. The way gravitational waves fell out of Einstein's equations decades before anyone detected them. The way Hawking radiation fell out of quantum field theory in curved space-time. A result Hawking himself found so surprising that he spent considerable time checking it for errors before publishing. The universe keeps having structures that the equations describe before observation finds them. Wormholes might be next, or they might not. But the pattern suggests that dismissing them entirely would be premature. There's a thought experiment that captures something important about all of this. Imagine that 1,000 years from now, humanity has developed a complete theory of quantum gravity, the successor to general relativity and quantum mechanics. A theory that correctly describes space-time at the Planck scale. A theory that has been tested to extraordinary precision, confirmed in multiple ways, accepted as the best description of physical reality. What would that theory say about wormholes? There are 3 possibilities. The first possibility is that the theory shows wormholes are impossible. That the quantum gravity corrections to general relativity, the new physics that only becomes relevant at Planck-scale energies, eliminate the wormhole solutions that the classical theory contains. That the smooth mathematical structures of the Einstein-Rosen bridge are replaced at the quantum level by something that collapses or becomes undefined. That wormholes are a classical artifact, a feature of an approximate description that disappears when the exact theory is written down. This is a genuine possibility. Physics has examples of this. The ultraviolet catastrophe of classical electromagnetism, the prediction that a hot object should radiate infinite energy at short wavelengths, was an artifact of the classical theory. Quantum mechanics resolved it by showing that energy is quantized. Wormholes might be a similar artifact. The second possibility is that the theory shows wormholes are possible, but only at the Planck scale. That quantum gravity produces microscopic wormholes as part of the quantum foam structure of spacetime. That they exist, as Wheeler imagined, as fleeting fluctuations at scales far below anything we could observe or use. That they're real, but permanently inaccessible. Part of the microstructure of spacetime that underpins the large-scale geometry we experience. This would confirm the ER equals EPR picture in a certain sense. Entanglement connections between quantum degrees of freedom would correspond to Planck-scale wormholes threading through the quantum foam. But macroscopic, traversable wormholes, the kind you could enter and exit, would remain impossible. The third possibility is that the theory shows macroscopic wormholes are possible, that there is a mechanism, currently unknown, that allows wormhole throats to be stabilized at scales larger than the Planck scale. That some effect of quantum gravity, some new feature of the theory that doesn't appear in either classical general relativity or standard quantum mechanics, provides the equivalent of exotic matter in a physically achievable form. That wormholes can form naturally under certain extreme conditions. Or that they can, in principle, be engineered, though the engineering would require capabilities that a technological civilization might eventually develop. Nobody knows which of these three possibilities is correct. The current evidence is insufficient to distinguish them. Theoretical arguments exist for all three. The physics community does not have a consensus on which is most likely. This is unusual. Physics often has rough agreements on open questions, even when definitive answers are missing. On wormholes, the disagreement runs deeper. This reflects the genuine difficulty of the question and the genuine openness of physics at its frontier. It's worth saying something about what the history of physics suggests about questions like this. When physicists in the late 19th century discovered that the classical equations of electromagnetism implied that accelerating charges should radiate energy and spiral into the nucleus of an atom in a brightest, tiny fraction of a second, they didn't assume that atoms must therefore be unstable. They assumed that the equations were incomplete. That new physics would save the atoms. They were right. Quantum mechanics was that new physics. When physicists in the mid-20th century worked out that the standard model of particle physics should produce Higgs bosons, they didn't dismiss the prediction. They built the largest scientific instrument in history, the Large Hadron Collider, to look for it. They found it in 2012. When the equations of general relativity predicted black holes, most physicists assumed nature wouldn't actually produce them. They were wrong. The universe is full of black holes. We've imaged them. The track record of the equations, when they produce something unexpected or uncomfortable, is remarkably consistent. The unexpected thing is usually real. Not always. Sometimes the uncomfortable prediction turns out to be an artifact of an approximation. But the default stance of physics, shaped by a century of experience, is to take what the equations say seriously, even when it seems strange. Wormholes are what the equations say. They've been saying it for over 100 years. The equations have been confirmed in every other prediction they've made. The honest position is not that wormholes are impossible. The honest position is that we don't know yet. And the history of physics suggests we should keep looking. there's a specific observational program worth knowing about. In recent years, several research groups have been working out the detailed observational signatures that different types of wormholes would produce. Not just what they'd look like in images from instruments like the Event Horizon Telescope, but what their gravitational wave signatures would look like. When two black holes merge, they produce a characteristic gravitational wave signal called a chirp. The signal sweeps upward in frequency as the two objects spiral closer, reaches a peak at merger, and then rings down as the resulting black hole settles into its final state. The shape of the ring down is called the quasi-normal mode spectrum. It's unique to the object's mass, spin, and the theory of gravity that governs it. For a black hole, as described by general relativity, the quasi-normal mode spectrum has a very specific shape. LIGO and its partner detectors have measured this spectrum in many mergers. The measurements match the general relativity predictions. But what if the merging objects were not black holes? What if they were wormhole mouths? Researchers have worked out that wormhole mergers would produce a gravitational wave signal that differs from black hole mergers in specific ways. The ring-down spectrum would be different. There might be additional echoes in the signal, gravitational wave pulses that arrive after the main merger signal, caused by waves bouncing back and forth through the wormhole throat. These echoes are a distinctive feature. Black holes don't produce them in the same way. Wormholes might. The detection of gravitational wave echoes in LIGO data would be a strong indication that some compact objects in the universe are not black holes, but something else, possibly wormholes. Researchers have looked for these echoes in existing gravitational wave data. Some groups have reported tentative hints. Others have found no evidence. The analysis is technically challenging. The echoes, if they exist, would be much smaller in amplitude than the main merger signal. Distinguishing them from instrumental noise requires sophisticated statistical methods. The search is ongoing. With improved detector sensitivity in future observing runs, the sensitivity to echoes will improve significantly. If wormholes are out there, and if they produce echoes in the way the theory predicts, future gravitational wave observations might find them. This is not speculation. It's an active research program. Papers are being published. Methods are being developed. The question is being asked with real instruments. And the universe will answer, in time, through the gravitational waves it sends us. There's one more connection worth drawing. One that brings together the quantum and the astrophysical in a way that feels almost too elegant to be accidental. Hawking radiation. When Hawking worked out in 1974 that black holes must emit thermal radiation, he found it by applying quantum field theory to a curved space-time background. He treated the quantum fields as quantum, but the space-time as classical. A semi-classical approximation. The result was that virtual particle pairs near the event horizon could be separated. One particle falls in, one escapes. The escaping particle is real. The falling particle is real. The black hole loses mass. It radiates. The radiation is thermal. Its temperature is inversely proportional to the mass of the black hole. Very small black holes are very hot. Very large black holes are extraordinarily cold. A black hole with the mass of the Sun would have a Hawking temperature of about 60 billionths of a Kelvin. Far below the temperature of the cosmic microwave background, the residual radiation from the Big Bang that fills all of space. So any stellar mass black hole in the universe is absorbing more radiation from the cosmic background than it's emitting in Hawking radiation. It's growing, not shrinking. The Hawking evaporation only becomes relevant for very small black holes, or for black holes at the very end of cosmic time, when the universe has cooled below their Hawking temperature. But the physics is real. The Hawking radiation is real, and it connects to wormholes in a specific way. In the ER equals EPR picture, the Hawking radiation emitted by a black hole is entangled with the interior of the black hole. The radiation outside and the interior inside are quantum entangled. By ER equals EPR, this entanglement corresponds to a wormhole connecting them. The radiation and the interior are connected by a quantum bridge. As the black hole ages, as more Hawking radiation is emitted, the entanglement accumulates. The wormhole connection between the radiation and the interior grows. At some point, a transition happens. The point at which the amount of radiation emitted is equal to half the original entropy of the black hole. This is called the Page time, after physicist Don Page, who analyzed it in 1993. After the Page time, the entanglement pattern changes in a specific way. The information in the black hole begins to leak out in the Hawking radiation in a form that, in principle, could be recovered. The wormhole connection reorganizes. The quantum geometry adjusts. The information is preserved. This is, in rough outline, how the ER equals EPR picture resolves the information paradox. The wormhole is the mechanism. The quantum bridge between the radiation and the interior is how the information gets out. Not in an obvious way. Not in a way that would let you read a book that fell into a black hole by analyzing the Hawking radiation. The information is encoded in quantum correlations so subtle that recovering it would require capabilities far beyond anything we could imagine. But it's there, in principle, preserved, not destroyed. The wormhole keeps the accounting straight. This is what wormholes have become in the most advanced theoretical physics. Not primarily a question about transportation, not a question about shortcuts between star systems, a question about what space-time is at its deepest level, a question about how quantum mechanics and gravity fit together, a question about the nature of information in a universe governed by quantum laws. The scientists working on wormholes today are not designing spacecraft. They're trying to understand the foundations of physics. They're trying to crack problems that have resisted solution for half a century. They're using wormholes as a mathematical tool to probe the structure of quantum gravity. And what they're finding is that wormholes keep showing up in the resolution of the information paradox, in the connection between entanglement and geometry, in the relationship between quantum information and space-time structure, in the behavior of black holes over their lifetimes. Wormholes appear again and again, in contexts where nobody initially expected them, doing work that nobody initially thought they'd do. This pattern is familiar in physics. When a mathematical structure keeps appearing in different contexts, in different calculations, coming from different starting points, and giving consistent results, that structure is usually real. It's telling you something about the world. Wormholes are telling us something about the world. The precise content of that message is still being decoded. But the message is coming through, clearly, repeatedly, from multiple independent directions. Physics is listening. What is a wormhole, really? It's a question the universe embedded in its own equations. It put the answer in the mathematics of general relativity in 1916 and waited for us to read it carefully enough. We read part of it immediately. Einstein and Rosen found the bridge in 1935. Morris and Thorne found that traversable versions might be allowed in 1988. Maldacena and Susskind connected them to quantum entanglement in 2013. The Google and Caltech team implemented the mathematics on a quantum processor in 2022. The gravitational wave detectors are searching for their signatures right now. The Event Horizon Telescope is refining its images of black hole shadows right now. The theorists are building quantum gravity frameworks right now. Every generation reads a little more of the message. And what the message says, so far, is this: space-time is not what it looks like. It's not a smooth, passive, fixed stage. It's a dynamic, physical structure. It responds. It bends. It connects. It contains tunnels in its geometry that have been there since the beginning, written into the equations before anyone was ready to understand what they meant. And those tunnels are not just a curiosity. They might be the key to understanding what space-time is made of. They might be the mechanism by which quantum information is preserved in black holes. They might be the geometric face of quantum entanglement. They might be the threads that stitch the universe together. Or they might be a beautiful mathematical structure that nature never bothered to build at scales we could ever access. Both outcomes would be interesting. Both would tell us something important. The universe doesn't owe us the answer we'd prefer. It owes us the truth. And the truth about wormholes is still coming in. One detection at a time. One equation at a time. One carefully confirmed prediction at a time. The same way every deep truth in physics has always arrived. Slowly. Precisely. From equations that had the answer before we knew the question. That's the nature of physics at its frontier. You don't get to choose which questions are answerable. You don't get to decide in advance which mathematical structures correspond to physical reality. You run the equations, you test the predictions, you look at the universe as carefully as you can, and you see what it tells you. General relativity has been telling us about wormholes for over a century. Quantum mechanics has been offering hints about negative energy and entanglement connections for decades. The combination of the two, pursued seriously, is producing a picture of space-time that is stranger and richer and more deeply connected than anyone expected. The wormhole is part of that picture. Whether it's a tunnel you could travel through, or a thread in the quantum fabric of space, or a feature of the mathematics that nature never builds at large scales, the physics keeps pointing at it. The equations keep returning to it. The research keeps circling back. That's not nothing. In physics, that's usually the beginning of something. And beginnings, in physics, have a way of turning into the deepest truths we know. The rest is time, and patience, and the willingness to follow the equations wherever they lead, even when they lead somewhere nobody expected. Especially then. The universe placed the answer inside its own equations. We are still learning how to read them. And what we've read so far is enough to know that the universe is not finished surprising us. Good night.